Hi, my name is Adi Sinha and I'm a research scholar at NC State University. Today I'll be talking to you a little about inspecting alternative decarbonization pathways for the United States energy system. Energy systems modeling has been described as a form of post-normal science where facts are uncertain, values in dispute, stakes are high, and decisions urgent. But at its bare bones, it's really just a linear optimization problem where the objective is to simply minimize the total system cost. These models have aided us in making decisions for long-lived infrastructure, and an example here is provided for the UK power sector, where on the y-axis here you have the total installed capacity, and the x-axis is the time horizon, and the different colors are the different kinds of technologies. This reflects a cost-optimal scenario for the UK power sector. These models are particularly important when now we are in the face of major shifts in the energy system and incentivized by decarbonization efforts by that 2050 time horizon. Cost optimal solutions, however, often miss difficult to model parameters like social constraints. And so this is what is illustrated here in these two figures where in the cost optimal scenario, ended up being quite different from what the real world transition looked like. And this is in part because of structural uncertainties that exist within the model, which are often difficult to capture in a mathematical sense. And these could include things like public acceptance to a certain technology, like nuclear maybe, which is just challenging to mathematically parameterize. One solution to this could be to look at the near optimal decision space instead of just looking at the cost optimal solution. And so the way you do this is by, in this figure here, you have the total system cost on the y-axis and then the decision variables on the x-axis. The blue lines show you the different constraints as part of the model, and the feasible region is highlighted in blue as well. Normally, you would run your optimization problem and come up with the cost optimal solution indicated by the red dashed line here. You would pull out the associated decision variables and call it a day. But instead, what we do is we provide a slack on the total cost, and then now we have this new space, this new solution space to explore. What you can now do is perform hundreds of iterations on this to generate a portfolio of decarbonization solutions instead of just living with the one cost optimal solution. Moving into some results. Essentially, this plot shows you the total fossil fuel use by different categories like coal, petroleum, and natural gas across the energy sector. As you would expect for a net zero scenario, you essentially see coal being phased out in the majority of our decarbonization runs. And if you were to break this down by the different sectors, it seems like the majority is in the electric sector, but again, phased out by 2050, and then some use in the industrial sector as well. Natural gas, on the other hand, has a different story associated with it. Particularly, it has a large, diverse range of futures by 2050. And this is essentially trade-offs against other technologies in those respective scenarios. Most of its use appears to be in the industrial sector. Now that we have these portfolios of decarbonization scenarios, we can try and identify illustrative pathways using clustering, specifically k-means clustering algorithms that can represent families of these scenarios. So essentially capture the characteristics of a whole bunch of scenarios as the centroid of that illustrative pathway. So what I'm showing now is the CO2 emissions by different sectors and by different negative emissions technologies for all of these, for some of these. So the first one here is looking at the net zero pathway for the least cost run. But we can also identify two new ones here which look at a case where there's low hydrogen and high hydrogen. And the high hydrogen, you can see, uses bioenergy CCS to form hydrogen. The captured CCS is used to form hydrogen. For low DAC and high DAC, it's a similar story with a lot of DAC use here, and you can see that their industrial emissions are higher in this case. And then finally, for electricity, low and high electricity as well. Um, with that, feel free to reach out to me with any questions you might have. And thanks to our sponsors for supporting this work.